Welcome to Lecture 30A. This is on Stokes' theorem, in particular superposition problems in 3D. The material covered here is from reading Assignment 5, Section 4.6, Problem 7, Cylindrical Geometries, Section 4.1, Planar Geometries, Additional Problems of Relevance in Section 6, Reading Assignment 0, Section 5.2, Lecture 1, Part A. So these are references that you can make use of, but most of this is coming from reading assignment 5. The objectives are to apply superposition and Stokes' theorem for a given magnetostatics problem, and the concepts and visualization skills contained within this lecture include a review of superposition principle and computational steps, determining the direction of the field and the functional dependency of the field's magnitude for each object, and also illustrate the procedure for determining the total field using superposition given two source-free objects. All right, as usual, the outline basically is a summary of the slides to follow. So we'll just skip over this and move on to the next slide. All right, so let's first discuss the notion of what we mean by symmetry. And since the types of problems that we're going to be dealing with here are limited, I'm just going to look at an example here, which is planar symmetry and cylindrical symmetry. When we deal with planar symmetry, we're talking about a plane of symmetry, and we're dealing with cylindrical symmetry, we're dealing with an axis of symmetry. So in this problem here, I've shown a cylinder and I've shown a plate. I've shown in the case of a plate a symmetry plane, which is this lightly blue shaded region, and an axis symmetry that passes right through the center of the cylinder. Here you can basically play with these P, R, and T sliders. P basically governs the movement of the cylinder, which is basically moving this back and forth. So the symmetry axis is changing its relative location. R is the movement of the observation point. This is where the observations are made at the point at which the field due to both of these objects is calculated. And T is the movement of the plane. So effectively this thing moving back and forth. The arrows that you see here, the black arrows from the origin to the observation point, the red arrow from origin to axis symmetry, and from the axis of symmetry to the observation point. So the distance from the origin to the axis of symmetry in cylindrical coordinates, basically this would be any plane that's parallel to the XY plane, and you're just dealing with what's the distance between the z-axis and the axis of symmetry. In the case of symmetry plane, it's with respect to the origin. It's to a point which is perpendicular to the plane, that is the plane of symmetry. Anyways, if you want to look at this, you can at this location here. This here sphere just means that you have the ability to toggle this. In the case of divergence theorem, we talked about spherical objects, but in the case of problems which are source-free, the notion of spheres doesn't come up. And so you can just ignore the meaning of this in the context of source-free problems. All right, we also have toroidal symmetry. The axis of symmetry, in this case, exists, and a plane of symmetry exists. So if you look at here, this base torus or donut, if you slice it right down the middle, it's like basically opening up a bagel. This is the symmetry plane. So everything above and below is basically a mirror image of each other. And the axis of symmetry is this vertical line that passes right through the center. Here you have an observation point, and then these various vectors representing the relative locations of the plane of symmetry and the axis of symmetry. The axis of symmetry is along a line which is parallel to the XY plane. And the plane of symmetry is basically, in this case, in the direction of minus z hat. And so this is the actual point at which we want to observe the field due to any form of current distribution that exists on this particular torus. So T here, basically, variable slider T, that's a black vector, that's the movement of the axis of symmetry that moves the torus back and forth like this. And the slider P, the red vector, moves this plane up and down vertically. The blue arrows from the origin to the observation point, and from the origin to the center of the toroid, and from the center of the toroid to the observation point. The red arrow is from the xy plane to the plane of symmetry, and the black arrow from the origin to the axis of symmetry. So these basic vectors will be used in the process of doing calculations where symmetry applies and where superposition is going to be imposed, because it's the only way to solve the problem. Anyways, you can look at this particular graphic at this URL here. Again, if you want to look a little bit more at superposition, you can review section 2.4 of Reading Assignment 5. Okay, so again, basic review of symmetry and the various computational steps that need to be followed. So if you have basically two source-free fields, so for instance, you have some form of a source. This is J1, it's a flux density vector. And here you have a different one, which is a flux density J2. In order to have a solution for the field, you need to know its curl and its divergence. And knowing symmetry will exist in this class of problem, it's relatively simple to determine what the vector field F1 would look like as a function of position in space. So this is, for instance, say a J1 due to a particular source, and this is a J particular to a second source. If I add these two together, right? So for instance, we know that if we take the field of this source, the field due to this source, and you add them up, this gives you the total field. This is a linear problem, and so if you were to take the curl of F, that would be the curl of F1 plus F2. This basically would be J1, and the curl of F2 would be J2, and the sum of these two, we can just give it an aggregate value of J. This is the total current flux density. The divergence of F0 will be equal to 0. So you can either take this as two separate problems, right? Solve each one of them independently and add the result, which is equivalent to trying to solve the problem as in total. Now clearly, this might be a very difficult problem to do, but if each one of these subproblems basically have a specific symmetry, then we are able basically to solve each one of these in turn. Having done that, we sum the results, and in effect, we're computing the solution to this problem here. Okay, so what are going to be the steps for calculating the total field F here? I've just itemized them. The first is to compute the field for each object, assuming that an axis of symmetry is aligned with one of the principal coordinate axes, or plane of symmetry is aligned with one of the principal planes. The reason we do this is because then we have a very standardized set of solutions, basically that we can make use of without constantly having to redo calculations. Second step is to convert each field into Cartesian coordinates. The fact that we're going to have to add fields means we can only add if we're using a reference coordinate system, and that will be Cartesian, because a Cartesian coordinate system basically is a linear space. So that would be the thing to do, and what makes it nice here is you could have combinations of cylinders and planes, and it doesn't matter because effectively you can solve an individual problem in a given coordinate system, and having done that, you can convert it into Cartesian. It's a relatively straightforward procedure. Third step is to transform fields to represent the physical location of the original objects with respect to a reference point, usually the origin, and to compute the field for each object at the observation point. So now basically we translate our solutions to the actual appropriate point, which is what we started with. And then the last step is to take those results and add them together, and that would represent the total field F. So this is more or less the procedure that we'll follow. All right, so let's start working on a problem, and we're going to look at a superposition example using Stokes' theorem. The problem statement is that you're given a current flux density distribution as follows. Z naught for x squared plus y squared plus y plus 2 squared less than or equal to 1. So that governs the current flux distribution in the cylinder, and it'll be pointing upwards. The next graphic will show that. On the other hand, if you're outside this cylinder, which represents this, then the value of the flux density is 0. For the slab, we basically have that as long as you're within the slab, there's a current flux density in the x hat direction, which would be in this direction. Outside, that is on this side or this side, there's no current flux density. The objective is to compute the total field F total due to these two current flux distributions at the observation point 2 minus 2, 2, which happens to be the point right here. All right, so what's the relationship between the equations and the type of symmetry? Well, the pictorial description to your left basically shows that. We're going to treat the blue slab and the red slab as independent objects. So we're going to solve for the field for this problem. We're going to solve the field for this problem. But we'll first make sure that we align each one of these objects with respect to the symmetry plane, or in this case with the axis of symmetry, which means that it's aligned with the z-axis. So that'll be the first step, but we'll deal with each one in turn. All right, so this just shows an illustration. This is an XY trace of the cylinder. So if we cut through, this basically is the direction of the current flux density for the cylinder. And this basically is a ZY trace of the slab. And you can see the arrows pointing in this direction, which is the current flux density for the slab. There's the URL here that you can click on. You can look each one of these objects. You can toggle between one or the other just by choosing either cylinder or slab. And T basically translates the cylinder and slab to the axis of symmetry, the z-axis and the plane of symmetry, ZY plane respectively. So this point is moved to this point, and this basically is moved to this point so that effectively the symmetry plane passes through the center and is aligned with the XZ plane. The black, as I said, the black arrows are the current flux density J. So this is just a picture showing the current flux density for the two separate subproblems. All right, so general principles when applying Stokes' theorem to solving source-free problems with a high degree of symmetry. All right, this is more or less a repetition from the past. I put this here just that it's in one location, but you should basically make sure you understand it. So here's Stokes' theorem. So this is a relationship between a closed contour integral and the integral over a surface bounded by that contour. And curl of f is equal to the j, and the j is given. So by computing the right-hand side, we're able to basically, in some way or another, extract f, particularly if symmetry in the problem applies. So here are the steps that we'll be looking at. We're dealing with right-handed convention when we're dealing with Stokes' theorem. The finger is the right hand pointing the direction of the tangent vector of the contour, and the thumb points in the direction of the area vector. J is given, so it's convenient to choose n to be in the same direction as j, in which case f is in the same direction as t. Again, the right fingers will tell you that. Choose NDS so that it's either parallel to j, in which case the integral of j NDS is easier to solve. You do not have to worry about the angle dependency between j and n. So this becomes a straightforward calculation in most cases. Fourth, choose the contour based on the following criteria. The vector field f is parallel to the tangent vector on the contour segment, and magnitude of f is constant each point on the same contour segment. Hence, f dot TDS is either the magnitude of f ds or minus magnitude f ds, and magnitude f can come outside the integral. So the objective is to make it such that the magnitude of f basically is outside, and then you're just doing a closed contour integration around the contour or a portion of the contour, depending on the specific values at different segments. B, vector field f equals 0 on the contour segment, hence f dot TDS equal to 0, simple. Third, the vector field f is perpendicular to t on a contour segment, hence f dot TDS equal to 0. So these are simple. You can just look at it by inspection and realize that for certain segments, the contribution to the closed contour integral will be 0. Next, the right-hand side of Stokes' theorem needs to be broken up into piecewise continuous region if j is not continuous. In our example, for example, j is not continuous, which means you have to deal with the interior region and you have to deal with the exterior region separately. 6 is for any given geometry, the left-hand side of Stokes' theorem needs to be computed only once and can be committed to memory, but you should state what you're doing without going into details. In the event that two or more objects of similar geometry, for example, nested cylinders, share the same axis of symmetry, there is the option to solve the problem as a single problem without resorting to superposition. You're probably just going through extra work using superposition in this particular case. You could just solve the problem as a whole. Okay, so now we basically go ahead and look at solving the field for the cylinder, applying symmetry. And what we do is we align the cylinder's axis with the z-axis. That was the first step. By the right-hand rule, J's cylinder points in the z-hat direction, so the fingers indicate the direction of the field. Choose a circular contour of radius r. First compute field exterior to the cylinder and then interior to the cylinder. And because symmetry applies, the field is in the theta hat direction. That's basically determined by just the right-hand rule. The fingers will basically be pointing in a counterclockwise direction when looking down on the xy plane. If you want more details, you can refer to section 4.2 of reading assignment 5, and the results more or less are summarized on the next page. All right, so now we're at a point where basically we can do the calculations for the cylinder, and they're basically going to be two steps. One is to compute the field exterior to the cylinder, and one to compute field interior to the cylinder. And so we start with Stokes' theorem. The closed contour integral on the left-hand side will be just 2 pi r times the magnitude of the field of the cylinder at a given radius r. On the right-hand side, we're integrating the current flux density, dot product with the differential surface area vector. We've chosen these to be in the same direction. So the differential surface area will be 001 RD theta. And J naught basically is already a given. This is in vectorial form. If we take the dot product and integrate, we end up with J naught pi. And so equating the left side with the right side, we can basically compute the magnitude F cylinder, and this just becomes J naught divided by 2R. Now we can also write J naught in terms of the total current flux passing through the cylinder. If we basically compute the total flux through the cylinder, then we get J naught pi r squared. This is just the cross-sectional area of the cylinder times J naught being a constant. Now, if the current flux density were not constant, you would have to actually do the integral. In this case, basically, it's a trivial answer. It's just the cross-sectional area times J naught. R is 1 in this example, so this result just becomes J naught pi. And so if we use I total instead of J naught, then we end up with this answer instead. So it's your choice as to whether or not you have it in this form or this form. It really doesn't matter. We know that because of symmetry, the field is pointing in the theta hat direction. This is the magnitude of the field, and therefore the field of the cylinder external to the cylinder is J naught over 2R theta hat. We now basically perform similar calculation, but interior to the cylinder. And everything is the same except for the limit now on the radius is from 0 to r, because r basically sweeps from 0 until r is equal to 1. Here, basically we went the full distance 1. Anything beyond 1 made no contribution because there was no current outside of r equals 1. And so we only have this integral to contend with. So in this case, the only difference basically will now be that this just becomes J naught pi r squared. Again, equating left-hand side with the right-hand side. The left-hand side did not change. We end up with this being J naught r divided by 2. Or if we want to put J naught in terms of I total, we end up basically with this expression here. The field is in the theta hat direction, and so we can now write this out in this form. So interior to the cylinder, the field is J naught over 2R theta hat. That is for r less than or equal to 1. If we now combine these two results into a compact form, the final result for the field of the cylinder is this expression inside the cylinder and this expression outside the cylinder. All right, now we look at the plane of symmetry. The plane applying symmetry, again applying Stokes' theorem, but to the slab now. Again, you refer to section 5, assignment 5, section 4.1 for more information about the slab geometry. So the method to compute the field F slab is first of all to align the plane of symmetry with the ZX axis. The right-hand thumb points in the direction of J slab. That's going to be the x hat direction because the current flux density is pointing in this direction, and the right-hand fingers indicate the direction of the field F slab. Remember that the field lines have to form closed circles, and so that means on this side the field lines are pointing downwards. At infinity they return, and they come up pointing in in the z-hat direction on this side. Because of planar symmetry, these field lines basically are parallel to the plane. All right, so this is explained here in terms of what you expect a field to look like, invoking symmetry. Then we want to choose a rectangular contour of height z, and we'll show on the next picture. And so first thing we'll need to do is compute the field exterior to the slab, and then the field interior to the slab. The reason we need to do that is because if you try to compute inside the slab, you'll have two unknowns, and you'll not be able to solve it. But if you can figure out what one of the unknowns is, then you can solve for the remaining unknown. And so the only way to do that is to first basically look at a contour which has one segment sitting on this side of the slab and one on this side of the slab. And because of symmetry, we know the field in this direction in magnitude is the same as the field in this direction in magnitude. And therefore, basically, there's only one value to compute, not two. So that's basically the way we're going to go. You can refer to reading assignment 5, section 4.5 for more details. It's, as I mentioned here, results are summarized on the next 3 slides. All right, so this is just a picture now showing how we're going to apply Stokes' theorem. This outside and inside refers to the vector field. So for instance, outside would mean, what does it look like outside the slab? If you click on this one, then you'll see the field distribution inside. The reason we don't have both on at the same time, there'll be too much visual clutter. Okay, so outside shows the field outside the slab, inside shows the field inside the slab. T varies the width of the area, that's shaded in red, bounded by the contour. So what's going to happen is that this segment here is moving outwards in this direction. So it moves all the way to the inside on this side and to outside on this side. The blue arrows, basically the current flux density. The gray arrows are the field vector. The orange is the differential surface area. We're choosing the surface area vector to be in the same direction of the current flux density as mentioned earlier. The red arrows are the contour segments, again, according to the right-hand convention. And the blue shaded area is the trace of the slab. Okay, of course, this extends to infinity in both directions. All right, so now, again, we're not going to go into details. This is for the exterior calculation. So in this case, what I've done is I've shown the contour segment such that it's just sitting on the surface on this side and just sitting on the surface on this side, and forms a counterclockwise pattern. According to the right-hand rule, n would be pointing in this direction. For the interior case, we hold one of the segments fixed on this surface, and we allow this particular segment to move back and forth, starting from the far left, moving to the far right. In this way, we can map out what the field distribution is inside the slab, whereas here we're only determining what is the field outside on the left and the right side, and it's uniform, again by symmetry, because the plane is infinite in size. So here basically is the calculation that we would do exterior. You have the magnitude F slab dz plus magnitude F slab dz. So there's a contribution on this side, a contribution on this side, no contribution here because the tangent vector is perpendicular to the field vector. All right, and so these two basically make no contribution. So you only have two that you have to deal with here. So these are uniform, so they can come outside the integral sign. So you end up with 2z fz. Now you do the right-hand side, which is basically compute the total current flux inside this area. And so this is from -1/2 to 1/2, and height z. The J slab has this value. This is the surface area vector associated with this. This is NDS. And so you're integrating this, and you end up with a value of 1/24. So now what you know is the magnitude, but you know that on this side it's pointing downwards, whereas on this side it's pointing upwards. So minus z hat in this side, positive z hat in this direction. And so that's basically what I've written out here, is that, you know, depending on where you are, it either takes on a negative value or a positive value. All right, on the interior, one side of the contour is lined with one face of slab, and the other side of the contour is in the interior of the slab. This is the picture shown here. So in this case, we already have computed this, so this is a known entity. We got this basically from this result here, and now it's this one we're trying to establish, depending on the relative position of y, which is how far is this segment away from this back edge. So basically we do this computation knowing what this is. You end up with fz times z, 1/24 of z. And now this, basically, we're going from minus 1/2 y to some arbitrary y. All right, and so y is now a variable, whereas before the y was basically, this y was 1/2, which meant was the whole slab. So we do the integration, j slab is this, and ds is this, and we do the computation, we end up with the result. So you equate this with this, and we find that f slab as a function of y, this is a scalar function, is y cubed over 3. And now we basically can put things together, and in vectorial forms, we know that it has a z hat. On one surface, it'll be pointing in the negative z hat direction, that is for y is greater than minus half. And at y greater than 0 and y less than a half, then this takes on a positive value. And so this is a compact way of describing the vectorial relationship for the field vector when you're inside the slab. So now if we put these two together, we can formulate the total field problem. So we have these three cases to consider. We have the inside the slab, to the left of the slab, to the right of the slab. And so this is basically is in an incomplete form now. So we have the field quantities now. Next. All right, so the next step is to convert the solution for each subproblem into Cartesian coordinates. In the case of the slab, there are no changes required because they were already in Cartesian coordinates. However, for the cylinder case, where we basically worked in cylindrical coordinates, we had the expression for cylindrical coordinates as being one expression for r less than or equal to 1 and one for r greater than 1. Now, to convert this into Cartesian coordinates, we basically make use of the relationship between theta hat and x hat and y hat, which is this expression that you see here. And r basically is just the square root of x squared plus y squared. So this is the equivalent expression for the field inside the cylinder in Cartesian coordinates. And this is the expression that we get for the field outside the cylinder in Cartesian coordinates. Again, for the slab case, we have three regions. We have the region inside the slab, the region that is less than minus 1/2 in the y direction, and the region that's y is just greater than 1/2 in the y region. So we have to translate field solution for each subproblem to the original reference frame. So for the cylinder, it's the difference between the original and a particular location, which with reference to an axis of symmetry or plane of symmetry. So in this case would basically be the position of interest. So we know this was originally y on the previous page, but if you subtract, you have y plus 2, and you subtract for the x coordinate, that's x plus 2. So that would essentially just mean x minus 2 is x plus 2, y minus 2 is y plus 2. So this is the actual field calculation now at the position of interest. And of course, these also get changed. This becomes x plus 2 and this one becomes y plus 2. And so now these are the translated versions for the field cylinder. And similarly for the slab, we have to translate back. In this case, this was translated by distance y equals 2. And so you can see this now as a y minus 2 factor in here, y minus 2 factor here. This will have to change because, of course, the relative position is different than when we solved it with the plane of symmetry aligned with the xz plane. Same thing here. So now all of these are exactly in the right position. And so the next thing to figure out is, well, where are we now? We're here. Well, this is outside the cylinder, and this is outside the plane. And so outside, in this case, for the plane would be on the left side, which means that it would be this one. As far as the cylinder is concerned, it's external. And so if it's external, it would be this one. So this is the one that we'll be using, and this is the one we'll be using when we do the summation. All right, so the last step is to compute the total field with respect to an observation point. And the observation point in this case are the coordinates 2, minus 2, 2. Now, since this observation point is exterior to the slab, It means that we only are considering the expression that relates to the cylinder, relates to a position outside the cylinder, and that corresponds to the expression that we see here. That's outside the cylinder. And so we just have to then substitute the values of 2 and minus 2 for x and y into this expression here. And if we do that, we basically find that the only term that survives are the terms involving the y component. And that can be seen clearly because if you have minus 2 for y here, this denominator will be 0. For the slab, it turns out the appropriate expression is the one where for y is less than 3/2 is when the slab field is minus 1 over 24 z hat. So there's no x or y dependency here, so we essentially have nothing to substitute. So we take this result and add the two together to compute the total field, which is shown here, and we end up with this result. Anyways, this ends Lecture 30A. Thank you for listening.